So, sorry that crashed there for a minute. So I'm gonna try this again. So we have a ball. So that's the boundary, and you can figure out the center. And then even if you have something like let's just say the map of the U.S. here, kind of funny shaped right there. You can figure out where the center is. You can make some measurements by on the diagonal and figure out where the center might be. So as long as you have a boundary, as long as you know what the border is, you know where the center is. So even when we talk about the United States, the contiguous 48 states, I think the center of the U.S. is actually in Minot, North Dakota. And so that would be the geographic center of the 48 states. So again, as long as you have a boundary, no matter what its shape, you can figure out where the center is. So the universe does not have any edges. There's no boundary. So so consequently there's no center to it. So each step in this ladder right here, we're going to cover each of these. So we're going to cover the edge and how we know that, and then why it gets dark at night, how the universe expanded. So we're going to look at all these different things here. Actually, we already looked at birth of galaxies, and curved space-time. We'll just barely touch on that because we don't want to do a lot of math here. So the edge center problem, is there a boundary and a center? So your textbook calls a boundary an edge. So let's make that clear here. So edge, by the term edge, edge means boundary. So it's not just, that's really important because so if you have something like this, this would be an edge right there, kind of like a cliff, kind of like if you had if this is the Earth here, or not just the Earth. I mean, if this is Philadelphia right here, you're standing in Philadelphia, and you climb a big hill, and you go out to that edge right there, and you're standing on the edge, and you're looking down. So you think where that would be Kelly Drive in Philadelphia, and there's all those rock walls up there. So you can kind of walk down. There's a cemetery up there, and you can kind of stand right out on that part, and you can look down at the street actually. So that would be an edge, and but it's also a boundary. You know, we see here's the clear delineation of the hill, you know, or the mountain, or whatever you want to call it. So the edge and the boundary does not have any edges. There's no boundary. So what specifies a clearly defined object. So there's no center to it. So there is no end in this ladder. There's no boundaries. You can't go out to the edge and fall off the universe. And how we know that? Nothing like that. And then so a galaxy, for example, the Milky Way, we saw that. We're going to look at all these different things here. Actually, we already looked at birth of galaxies, and then we had those swirling arms around there, kind of thing. We don't want to do a lot of math very well, but so the edge center problem, we could get to the point where we could say, well, this is the entire Milky Way galaxy. Calls a boundary. Something can fly out of it. Something can pick up enough speed to overcome gravity. So edge, by the term edge, and it may wind up over here. Edge means boundary. The universe is different. It's not just because there's no boundaries. You can't escape the universe because you're. So if you have something, so like everything, all of our planets, this would be all of our stars, right there, all kind of our cliff, galaxies, kind of like if everything is this is the universe here, or not just the Earth. I mean, if this is Philadelphia, and again, right here, you're standing in Philadelphia, no boundaries. You can't find a center to it. And there's no way to say where the center is. And you go out to that edge right there, and you're standing on the edge, and you're looking down. So you think where that would be Kelly Drive in Philadelphia, and there's all those rock walls up there. So you can kind of walk down. There's a cemetery up there, and you can kind of stand right out on that part, and you can look down at the street actually. So that would be an edge, and but it's also a boundary. You know, we see here's the clear delineation of the hill, you know, or the mountain, or whatever you want to call it. So the edge and the boundary are or what specifies a clearly defined object. So the universe does not. There is no end to the universe. There's no boundaries. You can't go out to the edge and fall off the universe or fall out of the universe. Nothing like that. So a galaxy, for example, the Milky Way, we saw that where we had a funny a funny looking center, and then we had those swirling arms around it, kind of thing. I don't draw very well, but we could get to the point where we could say, well, this is the entire Milky Way galaxy, and something can fly out of it. Something could pick up enough speed to overcome gravity and fly out of the galaxy, and it may wind up over here. So the universe is different, though. Because there's no boundaries. You can't escape the universe. It's all encompassing. So everything, all of our planets, all of our stars, all of our galaxies, of course, everything is in the universe. And again, consequently, because it has no boundaries, you can't find a center to it. There's no way to say where the center is. So Obler's paradox. Obler was a physician and an astronomer. So he was a doctor and an astronomer, a medical doctor and an astronomer. And his one of the things that he observed or came up with is that if there's no boundaries or no edges to the universe, and even if there were, when you look at the sky and you see all the stars, how come there's not this constant flood of light? Like, why does the sky get dark at night if you have stars and stars are light? Stars give off light, or they reflect light, really. It's the sun. Or no, I'm sorry, that's right. The stars are providing light, just like the sun does. So if you have all this light coming from all these distant spots in the universe, why isn't the sky constantly full of light? And so basically what he was saying is that if you're standing on Earth here, let's turn my pen on. So if you're standing on Earth right here, and the sun is over here, and we know the sun rises in the east, sets in the west. So let's just put the sun down here, and so it's throwing off some light here. But if you're standing over here on this side right there, it's nighttime. So when you're on that side, it's nighttime. And so the way the Earth revolves around the sun, you're going to be at night over on that side. But then you have all these stars in the sky over here. So why aren't they constantly illuminating the Earth? So really what that boils down to is, if you think of a forest and you're standing right here in the forest, every line of sight, everywhere you look, your sight ends on a tree. So you're in a really dense forest, and the trees are going to block your view. No matter what direction you look in, you look over here, you look here, no matter what direction you look in, the tree blocks your view. So all you see is this dense forest. So similarly, when the universe doesn't change and there's an infinite number of stars, we would expect to see stars in every direction. We would expect all the stars basically to obliterate our view of blackness or darkness. But really what's happening is it's more like a small forest, like the picture right here. So you can stand right here and you look here and see a tree, you look here and see a tree, you look there and see a tree, but you can look here and you can see the ocean right there. And you look over this way and you see nothing, or you see more grass and stuff like that. So really that's really what happens in the night sky. So if this is the Earth right here, this star right there, here's your line of sight, and the star's giving off light. But remember that light is a wave. So it's going to travel, and it gets weaker and weaker the farther away from the star it goes. That light wave gets really weak. So we're going to pick this up as a pinpoint of light, and then the same thing with all of these different stars. Even though when we look right there, the light is emanating in all those directions. The main bolt coming from the center, because of the massive distance between you and that star, you're going to see it as just a dot of light. You're not going to see the rays all dispersed like you do when you look at the sun. So that also leads to the conclusion, too, that like stars out here that are really far out in deep space, their light hasn't begun to reach us yet. So that depth of field, I guess to look at a universe like this right there, it makes the universe seem that it's maybe two-dimensional at best, that you're looking at a flat sheet with all the stars dotted, maybe a sheet of paper with all the stars dotted around it, and it ignores depth. So, but in this view here, when you consider like this view right there looks two-dimensional. They all look, like pretty much little dots there, and it's hard to see the depth. But again, like when you look in outer space and you look at the stars, the ones you see are fairly new. But the really, really old ones back here, their light that's farther out, their light isn't reaching us yet. So that's another reason too that the night sky is dark. So to summarize that, the night sky is dark because the stars, the light from that core of the star is so far away from us that by the time it reaches us in a straight beam like that. So and it's pretty much shown us as a dot, as opposed to the sun where you got all the rays emanating outward, and we can't see the individual rays, but we're close enough to the sun that all of the light emanating from the sun bathes the earth when we're looking directly at it. But then when we rotate away, if you're over here with the sun, you're going to be illuminated, but back here, the light can't wrap around and illuminate. It's going to dissipate by the time it gets there. And then another reason too, again, is that there's a lot of distant stars further out whose light hasn't reached us yet. We can't see them yet, or we can't see them anymore. Maybe they're so far away and so dim that we can no longer see them. So the universe, a common misperception is that the universe doesn't change. I don't know why that's a misperception. We know that stars die and stars are born. So the truth is that the universe does continue to change and evolve. Eventually, probably not in our lifetime, constellations like Orion may cease to exist. Those stars will burn out. So we already studied star birth and star death. And so that tells us alone that the universe is going to continue to change and evolve. We also know, though, that the universe continues to expand. And it's going to continue to expand as though it's being stretched. As like if you took a rubber band and you stretched it, you're going to make it a bigger one. But a rubber band has hollow in the center. A better thing it would be like think of like pizza dough. And it starts out in a ball, and you keep pounding it and you're stretching it, and you can keep flattening it and flattening it out. And that's more like what the universe is. It's more stretching. Another way to think of it too is a photo. So if you have a photograph that's a 5x7, and you want to enlarge that photograph and make it an 8x10, everything gets enlarged and stays within proportion. So perhaps that's not the best analogy, because we know with the universe, when the universe stretches, it creates a greater distance between like the Earth and the Orion constellation. So it creates the impression, the universe expanding creates the impression that galaxies are flying further away from each other, when really it's just that because the proportions are stretching, we're getting a greater distance between 2 points. So I guess if we go back to the picture analogy, so here's the now we'll just stick with that. We'll stop with our picture. So again, the universe, it's a misconception that the universe is changing. We want to remember that the universe does change and evolve. And that evidence for that is that new stars are born and stars die. So the expansion of the universe led cosmologists to conclude that the universe must have begun with some kind of an event of unimaginable intensity. When we figure out, when cosmologists and astronomers, when they figure out that planets are billions of years old, or tens of thousands of years old. When you figure how old that, or how long that really is, for the universe to still exist, but for the planets to still exist, there must have been an event that was so intense and the energy is still present from it. Normally, when you think of somebody, normally when you think of like run, or climb a flight of stairs, and you have all this energy, and you get up to the top of the stairs, and you've expended some of that energy. Maybe you're short-winded. Maybe you climbed 5 flights of stairs, and you're short-winded, so you dissipated a lot of energy. But for the universe to still be existing now, and the sun still shines, and the Earth still is rotating, when none of the planets have collided into the Earth yet, none of the planets have collided into the sun yet, or anything like that. So really, when you think about the universe existing now, and 14,000 years ago, or even longer than that, a million years ago, or pretty far back, the genesis of the universe, there must have been a pretty major event, pretty intense event. And we'll see a little bit that intensity is due to gases, very high temperature gas. So it's no longer a hypothesis that the universe is expanding. There's a lot of evidence, a lot of solid, comprehensive evidence to say that the universe is actually is still continuing to expand, and we'll be able to show that in a little bit. So the necessity of the Big Bang, your textbook uses that term, but it's not really a necessity. What we're really saying here is the necessity of a really major event to set things in motion. So the perception that galaxies are moving away from each other with a speed proportional to distance, there must have had to have been a beginning when everything was concentrated in one single point. And so that would be where all your galaxies. So like if we say all your galaxies and everything were all kind of clustered right here, and then something happened and made everything start moving away. So when just one little before we move on to the next slide, we have a little definition here. So the estimate of the estimated age of the universe, that's called Hubble time. So a little definition right there. So the misconception, so we know that the universe is expanding, but we don't want to say that galaxies are actually flying away from the location of the explosion. That's actually two misconceptions here, or that the Big Bang exploded, that we had this cluster, of stuff, and that there was an explosion. And the explosion, from the core pushed everything out. So there was no explosion. So, there's no explosion. And then consequently, the galaxies are not flying away from the location of that explosion because there was no explosion. So the truth is that the Big Bang filled an entire volume. So the universe really, at one point, the universe was really small. It was very compact. So I'm just going to show boundaries here, but because we're talking about volume here too. So just keep in mind, though, that there is no such thing as a boundary around the universe. But if the universe, what we can say, though, is that the universe at one time was really small. And the Big Bang, instead of starting at the center and pushing out, basically everything was the universe was so compact and everything was in such close proximity that meant the temperature went real high. So when you build up a high temperature, you create a lot of pressure. So at every point in this universe right here, the temperature rose and the pressure built up. But instead of exploding like an egg, so our little egg theory here, that's not in your textbook. But the egg theory here, it would be that you just imagine an egg. You have a shell and then you have contents inside the egg. So if you keep heating and heating that temperature, or heating and heating that egg, the internal temperature is going to get real hot, and the material inside a lot of pressure is going to build up, and eventually the shell cracks. But with the universe, if you think of the entire volume of the universe maybe being the size of an egg, instead of that shell cracking, rather the high temperature melted it away, and it just melted it uniformly, and then the universe began expanding. So there really was no big explosion. The Big Bang was that all this pressure built up, and then the pressure under that high temperature, made this like boundary or volume begin expanding, and it just kept expanding and expanding and expanding, and consequently we get stars farther and farther out. Stars are born farther out, and you have a lot of gas out here that makes the stars start forming. So you just had a lot more area to cover. So and that alleviated the pressure. So the evidence for this is that the planets like some of our farther out planets, we have like Neptune and Uranus. Those two planets are pretty far away from the sun, and they're really cold. They're very icy. So they must have cooled off. If they formed initially, and we'll see how they all initially formed around the sun. So we had these little rings here, and then the planets formed, and all that gas, they used up all that gas to form, and now they there's pretty layers out. So because these are so cold, we have like minus 600 degrees down here, versus Earth, which has normal atmosphere, maybe 100 degrees is going to be really hot. But when we look at 100 degrees compared to minus 600 degrees, obviously very cold out there. So those planets started cooling off. So that's how we can tell too that the Earth is expanding, and that temperature is no longer uniformly hot everywhere. We see the sun. Obviously, the sun's extremely hot, but the Earth is not. And then we get all the way out here to a very cold environment. So that change in temperature, that big temperature drop, it leads to the conclusion too that the further away, the more the universe expands, the cooler it gets, the further away you go from the sun. So the radiation from a very early phase of the universe is still detectable today. So that's another way we know that the universe is actually expanding, and that there was no just gigantic bang from a core. So basically all this material here, and so the radiation from a very early phase, we can actually detect it today. So it came all the way to the Earth. There's a little bit when we look back in time. So this look back right here, look back in time, we can see this little bit of radiation. But you don't even have to look back. You can read in your textbook the two guys that won the prize in the Nobel Prize in physics. They came upon. They were looking through an antenna, and pigeon droppings fell in the antenna, and they cleaned it out, but they still saw the same image. And they saw like one little band that they thought was light, and they couldn't make out what it was. And eventually they figured out that it was radiation from a very early phase of when the universe began. So that background radiation, it has a black body spectral distribution with an apparent temperature right here. So why that's significant is the universe, when it was all pretty much all back in here, it was a black body, so they don't emit light. And then when it started expanding and light was absorbing before, and now light is being emitted, and a little bit of that radiation from an early phase is still detectable today. And the neat thing about that James Webb telescope that you did in your project, that's expected to be able to look so far back in time at the beginning of the universe to really figure out a lot more about this Big Bang theory and the creation of the universe. So a lot of exciting developments in astronomy and cosmology. So here's a little bit of a look at the microwave background. So we can see here's our microwave image of the universe. You can see infrared imagery, things like that. So the intensity initially at the beginning, here's the beginning of the universe right here, would have been really high in intensity. But now it's dropped off, and again, that wavelength, the further away you go, the weaker it gets when you're over here on Earth detecting that signal. So at 1/1,000,000th of a second old, when the universe was that new, at 1/1,000,000th of a second old, the universe was filled with high energy photons, and the temperature was, let me look that up. I didn't realize that got messed up there. So this temperature should be, it should be 2 times 10 to the third Kelvin, and this should be 2 times 10 to the 12th Kelvin. So the universe, at birth, the universe was filled with high-energy photons at a temperature of 2 times 10 to the third. So the photon would need enough energy. 2 photons, if a photon has enough energy, 2 of them can convert into a pair of particles. And that's what happened with, they became a proton and an electron. And so it's basically the same thing as matter and antimatter. I think your textbook refers to protons and electrons as matter and antimatter, with I think matter being the electron. And then if matching and meeting together, the 2 particles can actually cancel each other out and convert into a gamma ray. And then at 10 millionths of a second old, the temperature actually was a little more intense there. So it was getting hotter and hotter. But then a few minutes into the birth of the universe, you have those pairings happening, that matter and antimatter, and you end up with hydrogen starting to form. And then now you get helium. So you get 1 hydrogen atom, 2 hydrogen atoms, 3 make helium, 4 is helium, and then you just keep getting them combining, and you get all these different particles that are now being made at the birth of the universe. So during expansion of the universe, the radiation and matter cooled, and at a rate that was set by the expansion rate, so proportional to that expansion rate. So you got your new particles over here. You got all these new particles, and they're dense ionized gas, but then they start moving away, or they start expanding, but more stuff is filling in over here. But you're getting more and more particles now. So in the neutral gas, after recombination, you get a lot of different matter now, and you'll start to see that rocks are going to form. So the density of the energy in the form of photons became less dense, became less than the density of the gas, and continued to recombine. Protons captured and held free electrons to form a neutral hydrogen atom, and then the reionization started, where the first stars formed, and that ended the dark age. Stars now give off light. So the universe is isotropic, which means that the physical properties are the same regardless of the direction in which you're measuring it. So no matter where you measure the sun, it's going to have the same intensity or the same brightness. And an isotropic property is measured on all axes in all directions. So if we just look at 3 axes right here, we have X, Y, and Z. So no matter how you measure the sun along one of those axes, you get the same answer. And the cosmologic principle is that any observer in any galaxy sees the same general principle for the universe. So there's no special place where the universe is different. So people in England are going to observe the same things that people in America observe. So no matter where in the world, no matter where on Earth you are, you're going to look at the universe in the same way. Similarly, if there was life on other planets, they'd be viewing it the same general properties as well. And then, so that's another reason or another amount of proof that the universe can have no center or edge. So another misconception is that redshifts are actually Doppler shifts of galaxies flying away in space. But the truth is that galaxies are separated from each other as the space-time expands. So as the space expands, so if we take a piece of paper here and we expand that piece of paper, we have 2 galaxies really close. Now we have them far away, and then we expand it yet again. We have those same 2 galaxies. So here's the space that got stretched, and then time. As time goes on, maybe we start out at 1 minute, and then here's 2 minutes and 3 minutes. So as time increases and space increases, we get greater distances between the galaxies. And then the photons from the distant galaxies spend more time traveling through space, and consequently they have a larger redshift than a photon from a nearer galaxy. So we still have some matter in outer space, though, or in the universe, because we have some of that blackness there, and we still have some gas. So the expansion is in fact accelerating. It's not slowing down. The universe is not going to stop growing. And so that means that there's some type of energy in the universe that's pushing on space, acting against gravity. And that energy is called dark energy. So the dark energy is associated with the cosmologic constant WL. Oh, sorry about that. I'm sitting here reading off the slide, and I just realized I made another mistake. My package, my Explain Everything EDU, doesn't look at Greek characters, so it's actually omega A. I just paused that. As soon as I said WL, I was like, wait a minute, something doesn't make sense. I never heard that. So omega A, or omega sub A, is the actual constant that's associated, or is a measure of the dark energy in the universe. So knowing that there's dark energy, that changes the possible outcomes for ways of looking at the universe. Instead of thinking that it's contracting, knowing that there's dark energy and that it's always kind of pushing on the stars and star clusters like this one here, it means that it makes the presence. It means that the presence of gravity is being counteracted by this dark energy, because gravity would tend, like we know on Earth right here. If we're on Earth, gravity pulls you to the core. So if without this dark energy, the universe would be shrinking and everything would be collapsing in on it. So instead of starting out as this real tight-knit volume that expanded and continues to expand, rather we would have a shrinking. We would be going back to that dense volume of high temperature. So that high temperature, high pressure overcame the gravity inside that volume, and the dark energy continues to overcome the attraction of gravity, and it continues to make the universe expand or accelerate away, or accelerate that stretching. So the nature of dark matter, recent estimates are that it's about a factor. So again, this is our omega, and then this right here is your omega, the amount of mass. So your intensity is about 0.7 and your mass is about 0.3, and that comes to a total of 1, and that gives you that indicates that the universe would be flat. So the universe is accelerating, and it's going to continue expanding forever because you have this dark matter there that's going to continue pushing out. If the dark matter went away, gravity would win, it would contract. So the estimate of this dark matter indicates that the universe is going to continue to expand. And the expansion is actually an acceleration. It's actually moving faster and faster. It's not inflating. That's a hypothesis that says the universe went through a brief moment of super expansion, like when you're blowing up a balloon. And then when it was a tiny fraction of a second old. And so if you think of blowing up a balloon, you get that initial really easy time when the balloon is flaccid and you start blowing into it. You get a really big expansion, and then it gets harder and harder to expand the balloon. So that's what the inflation hypothesis was. But the universe actually has been expanding at the same rate. So there was no initial big bang or big inflation either. And then an accelerating universe moves pretty much along the line, this orange line, but a decelerating universe would be more along that blue line. And we're able to take measurements here to see that things are moving farther and farther, like certain stars move farther and farther. And the light or the red shift of it indicates greater distances occurring between objects in the universe. So another explanation is that acceleration could be caused by a cosmologic constant, but that's pretty much what the nature of dark matter really is. But here, another explanation is that it's an anti-gravity force as part of the fabric of space. But really, that just leads back to the conclusion that the dark energy is what's driving that acceleration. Quintessence means that there's totally empty space, that it's a vacuum. and that's what contains the energy that drives the acceleration. But that's really, you see a vacuum in outer space, but you don't see a vacuum on Earth, and yet outer space and Earth are part of the universe. So quintessence doesn't really hold much water, so everything really gets back to this dark energy as the accelerator, or what's making the universe expand. So some visuals here of the expansion, or that acceleration's happening. And so you basically see a variety of different images and changing shape and size, and moving with space, increasing amounts of space between them. If there was a switch from deceleration to acceleration, you would see what they call the big rip. And that's not happening. Basically, what we're observing is this constant blue line out there. So dark energy overcame gravity at that point, and that's when the acceleration continued. And it happened about 6 billion years ago. So if you want to say the Big Bang occurred, so you can see expansion. You see a little bit of a slowing down of expansion, but then you see it changing speed, and that's okay. It's not necessarily contracting. It's just that the expansion isn't moving at a constant rate of acceleration. But then you see the deceleration, where it gets a little slow right there, ripping off, and then consequently you get a constant rate of acceleration now. So if the expansion of the universe has been accelerating, it must have been expanding more slowly in the past. So that's another postulate, but that time estimate, the Hubble time estimates 14 billion years. But the ultimate fate of the universe really depends on the nature of that dark energy. If by some chance that dark energy evaporates, if it's not limitless, then the universe will cave in on itself. Gravity will pull it in. The big rip, whether it happened or not, it's still a possibility to happen again. The inflation theory encountered two problems, flatness and the horizon. So inflation would, like you inflate a balloon, that requires a boundary, but the universe has no boundary. And then the universe is also flat. There's really, how do you inflate something that's flat? So the key to solving the inflationary hypothesis was that there was a sudden and temporary episode of rapid, enormous expansion when the universe was young. But that would mean that you blew up a large balloon, and then eventually the balloon ripped or flattened somehow. And it's just a lot that doesn't really make sound scientific sense when you look at it in terms of the balloon or inflation theory. So back to putting all this together, the universe should be extremely close to exactly flat. A little bit of curvature there in space-time over greater distances needs to be determined still, if there is any. And then a sudden expansion would produce gravity waves that would leave traces in the cosmic microwave background that we're still able to see. But we don't see that. So but that doesn't mean it's not there. There's still a search for small variations in that background to see if there is any leftovers of some kind of a gravity wave of some sort. A lot of misconceptions again. Explosions. Another misconception is that an explosion would produce sound. But the truth is that there's no sound in space today, and that's because there's nothing in outer space that vibrates to cause sound. Sound is caused by vibrations, just like your voice is caused by the vibration of your vocal cord. However, when the universe was young, it was dense enough for sound to travel, and so the Big Bang actually did make a noise. All that densely compacted material was close enough to vibrate, and you could hear that sound. So those sounds produced irregularities in the cosmic background. And of course, if you have any questions, please do reach out and ask.